My name is Adam Su.
I'm Sodhi Chowdhury.
I'm Patrick Wu.
We'll be presenting elementary proof that kappa surfaces have bounded integral curvature. This is a project that we conducted during Stony Brook's 2022 Enhanced RU program. It's a year-long. It's a year-long program. Yeah.
It's a PDF.
Yeah, so there's the chance, gives sophomores and juniors a chance to do and learn about research in an area of math. Our specific area was metric geometry. We worked under Professor Matthew Romney. He is a postdoc here at Stony Brook. And we studied a specific kind of subfield that dealt with geometry known as an Alexandrov space. So, yeah, during the RU program, we had some highlights. We were able to go to New York City and have a school-sponsored meal at a nice restaurant. And then we also went to the MAA Math Fest, and this guy is our mentor, Professor Matthew Romney, and he actually did a RU program under his mentor, which is Professor Michael Dorff at BYU, and that's what kind of got him into the math research area. Yeah, and then the last kind of story I have is we originally thought that we would be able to find our results in a German paper by the guy who founded the subject, Alexandrov. We were able to locate the paper after a couple weeks of just just looking for the paper, but actually didn't have exactly the result we wanted, but we translated the paper and it had a couple of results that were actually pretty interesting still, just for the subject in general. And it's interesting because a lot of results in this thing were in Russian or German, and we're kind of because that's where the subject kind of originated. Yeah, question?
Why did they say Leningrad in German?
He wrote in so Alexandrov was based in the Soviet Union. Yeah.
But why did he want to write in Russian?
Well,
I think it's because like pre-World War II, the official language of mathematics is German. So like the center of math is in German, and English only comes into prominence after World War II, after devastating Nazis.
Yeah. Okay. So yeah, so you can
all right.
you can start the chalkboard part.
Yes. So I'll be giving on some background information regarding Alexandrov geometry. I know it's really obscure. I would say most people never heard of the name. So we all learn geometry in high school, right? So you have the Euclidean classical plane geometry. You're looking at triangles, like whether they're congruent. You're drawing parallel lines, etc., etc. But the modern way to do mathematics, to do geometry, is use calculus. So you basically have differential geometry that you're doing analysis on general spaces called manifolds. So I don't want to get into the situation here, but the point is you need to use you basically need to use coordinates and do calculations. You integrate over differential forms, etc., etc. And Alexandrov geometry is also a study of geometry, obviously, but its approach is very different from the now commonly accepted differential geometric approach. So basically, what are the important concepts in classical geometry? We have length, right? So we are looking at the distance between points. We have angles. So if we're given you have two lines, then you can define an angle. 2 segments, you can define an angle between them. And these concepts don't really get used in differential geometry, but in Alexandrov geometry, they are essential. So why do people want to study Alexandrov geometry? Basically, because we don't need calculus, right? You recall that to use calculus, the functions you are looking at must be very nice, like they have to be differentiable. So for example, you cannot have some sharp points that are just badly behaved. However, with Alexander geometry, you can study these kind of spaces. They call singular spaces, and that makes it very attractive. All right, so the basic setup is this. We're looking at a metric space X. Metric space. Recall that a metric space is basically a space where you can measure distance between points. And this is 100% a metric space. It's actually, we call a geodesic space, a complete geodesic space, that we can, for each pair of points, X and Y, we can connect them with a curve such that the length of the curve is the same as the distance between X and Y. So with the geodesics, we can basically generalize the notion of a straight line in Euclidean geometry to arbitrary spaces. So now we have the concept of length. I'm going to define the concept of an angle. So if you have a triplet of points, so P, Q, and R, and the geodesic could look very different from a straight line. But you can define a triangle in the Euclidean plane just by requiring that the distance between the length of the three sides is the same as the length of these three sides. So you have P bar, R bar, and Q bar, and such that we require that the distance between P bar and Q bar is the same as distance between P and Q. This is called the comparison triangle of this triangle. And now we know that in Euclidean geometry, a triangle is uniquely determined by its three sides. So you have like three sides. If the three sides are the same, then but they have to be congruent. So there's a unique one. And we can kind of define the angle of Q, P, and R. We can define this angle. Our initial idea would be defining this angle as this angle here, but this is actually not very good. Instead, we have to take limits. We have to. So if we're given two geodesics, just P and PQ and PR, the trick is we look at a limit of triangles as the points gets close to P. And for each small triangle, you have a corresponding angle here. So we define the angle between PQ and PR to be the limit of this angle, to be the limit of a shrinking comparison triangle. Okay, so why am I spending so much time here? Because the angles in a general Alexandrov space might look very different from an angle in the classical Euclidean space. For example, if you're having a geodesic here, so this is the length minimizing curve. This is a unique geodesic in our metric space. What's the angle here? If you just add a vertex here, what would be your guess? What's the angle? Yeah, it will be 180. This is a theorem. This is like the angle between, if you have a geodesic, the angle it makes is 180 degree. Right now you draw out a line. You find another geodesic out of it, and now you look at the two smaller angles. So this is alpha. I call this alpha. Call the other beta. What would be the sum of alpha and beta?
Well, if you split the 180-degree angle into angles alpha, beta, it's 20 degrees, right?
No, it's not. Actually, it's not. In a general space, we have the angle inequality here. So we know that alpha plus beta is definitely greater than pi over, no, it's pi. Right. It's definitely greater than pi. However, you can have situations where the two angles, the sum of two angles is greater than the total angle here. So example would be, so if you consider the plane, you remove this region. So you basically remove a part of the cone. And then you only remove the open region here. So like these two lines are still inside your like metric space. And you keep the space, the usual metrics, like distance on the plane. It's a different color. Right, so now you consider an angle here. Angle looks something like this. What's the angle here? It's actually 180 degree. Why? Because this is a geodesic. This is the shortest curve joining these 2 points, right? Because you remove the middle part, so you can't just go from here to here. The straight line doesn't come through, so you have to take this path. And this is the shortest distance between these 2 points. This is the shortest curve between these 2 points. So the angle here would be 180 degree. And now you draw a geodesic out of it. So what is this angle? It's not. This is not, well, this is not a geodesic, but
But then both of them geodesic?
what? This?
Both, yeah, they're geodesic.
No, this is not geodesic,
Okay.
because this is the geodesic joining these 2 points.
Oh, sure.
Yeah. But if you do the limit procedure I described earlier, like you look at like successively smaller triangles, you will find that this is just the usual Euclidean angle. So it would be, I don't know, I would take 120 degree. That's definitely greater than 90. And what's the angle here? Obviously it's also 120. So the sum of these two is greater than 180. However, we can prove that the bad case only happens if the larger angle you are looking at is pi. So if the angle like, so if you have some angle that's like smaller, if the total angle is smaller than pi, then alpha plus beta is actually equals to the larger angle. Right. So, right now we have the basically set up metric geometry, so we can talk about length and angle in a general metric space. We're getting into Alexandrov geometry. But first, I'll talk a little bit about the concept of a curvature. So what is the curvature? I don't know if they teach this in calculus or anything. You might be in multivariable calculus, but you can calculate the curvature of some curve, right, by choosing a parameterization, and you do some calculations like take differentials and all that. So that's the classical concept of curvature. In modern differential geometry, you can also define a curvature, but you're using the what we call the Riemann metric tensor, and then you need to like use up this really complicated object. You have like scalar curvature, you have sectional curvature, but the idea is to measure how curvy the space is. So for example, if you have a circle, the curvature in the usual use method would be the reciprocal of the radius, if I remember correctly. I don't remember correctly. And the Euclidean plane is flat. In differential geometry, so for each point you have a definite curvature tensor. But because I said earlier, Alexandrov geometry, you don't have all this like calculus to use at your disposal. So what do? So instead of looking at a definite curvature at each point, we're looking at a global curvature bound. We're just gonna write here.
Erase that left part.
Yeah. Right. So I said earlier, like we're comparing triangles in the metric space, we're looking at and a triangle in the plane, right? So this kind of comparison is very useful in Alexandrian geometry. So it'll take some time to introduce the model spaces. What are model spaces? These are surfaces of constant curvature. So for surfaces of constant curvature, if you're just looking at compact surfaces, then there's a theorem, it's not used pronunciation, but all compact orientable surfaces can be classified by their genus. But the thing I'm using here is that the only constant, the only surfaces of constant curvature are the sphere, two spheres of different radius, the Euclidean plane, it's not compact, but and the hyperbolic disk. So there are three kinds of spaces. Right. So the curvature I will call is kappa. So this kappa is greater than 0, and you have the plane. Kappa equals to 0, and the hyperbolic disk. Something like that. So now instead of just looking at comparing triangles between our space and the plane, we're comparing triangles with with spherical triangles or hyperbolic triangles. So if you read some popular math, it is often said that like a spherical triangle is fatter than the usual triangle in the plane, meaning that the sum of the three angles will be greater than pi. And if you're looking at hyperbolic triangles, the sum of the three interior angles would be less than pi. So in some sense, the angles measures the curvature of the space. Another erase this example. Right. So now this definition. The space X is kappa. So this is the definition here. If for each triangle delta, let's call it PQR. The corresponding triangle in the model space satisfies the following condition. So if we draw out a triangle, so this is our triangle in the space, in the metric space we're looking at, and here I will pretend that this is a triangle in the model space I introduced there. So the surfaces of constant curvature. And we require that PQ is the same as P bar. P bar, Q bar, the distance between P bar, Q bar is the same as the distance between PQ, so it's a comparative triangle. So if I pick any 2 points here, call this X and Y. Now because the distance between these two are the same, so I can find corresponding comparison points. X on, I should say this is X bar, Y bar. X and Y here. So X and Y uniquely determines X bar, Y bar here. If I draw a geodesic between them, I require that the distance between x and y is smaller, no greater than the distance between x bar and y bar. So it's d of x, y bounded by d of x bar, y bar. Okay. Now, if, I think using a version of law of cosine, you can show that this is equivalent to requiring that the angle here to be smaller than the angle here, if I remember correctly. This one is the definition we work with. So the definition of kappa really says that the triangles you have in your space is not fatter than the triangles here. So by not fatter, we mean that the distance between a pair of points on the edges only shrinks if you really get into your space. So this is not fatter, this is fatter. This is called cat kappa. This cat, it has nothing to do with an animal. I think it's an acronym named after 3 mathematicians. C is Cartan, A is Alexander Roloff, and T is, who is T?
I think it's tits.
Tit?
Yeah.
Okay. Alright. Alright, so I think this name is coined by Roloff. And by the way, I think you people all know that Perelman, who proved the Poincaré conjecture, right? The Russian mathematician Perelman. But very few people know that he actually started his career in Alexandrov geometry.
Oh, well, I'm wrong. It's Topogonov.
Topogonov makes more sense.
Yeah.
No, Tis is actually a valid method.
Yeah.
Yeah.
Because they have like tits buildings and then. Those are an example.
The top one term you should not Google. Okay, but where am I? Alright, so this is kappa, so curvature bounded from above. We also have another notion of curvature bounded below, where you just reverse the inequality. Actually, for the curvature bounded below case, there's a lot more literature. So our project, what we've proven is there's an analogous statement in curvature bounded below case that is proven in, I don't know, 1990s or something. This kind of classical aspect. But this is a new proof. But the one we're giving is seems like a new proof in the literature. Alright, this is kappa. Okay. And finally, I'll say so our project proves the equivalence of two, not equivalence, but one condition of curvature bound implies another. So this is for first curvature. This is the first curvature bound we're looking at. And then I'll talk about another curvature bound. The second bound is called bounded interval curvature. Right, so what is this? So instead of looking at just like one triangle, we're looking at a collection of triangles. So, so on the sphere, by Girard's theorem, or you can, if you really like it, you can use Gauss-Bonnet theorem, the area of a triangle, the area equals to curvature times the angle access. Did I remember this correctly? Curvature is times area. Oh, a mistake. So what is the angle access? It's the difference between the 3 angles minus pi. So it measures how different the triangle is from a Euclidean triangle. So in some sense, if you have so the angle deficit is related to the curvature. Now in a general space, we're looking at a collection of triangles. So let's say this is an open neighborhood, an open set. We're looking at a bunch of triangles. And we require that they do not intersect each other. They're disjoint. They have disjoint interior. And we sum their total access. This gives you a sum. So if you have so if you're on a smooth Riemannian manifold, then for example on a sphere, then by this formula you will know that the sum of their angle access is just kappa times the sum of their area. But their area is bounded by this larger neighborhood, assuming it's finite. We can always find a neighborhood such that area is finite. So this is bounded by kappa times some constant here. So this shows that if you're on a sphere, then the sum of angle deficits of collection of triangles are bounded by some constant, and this constant doesn't depend on your triangle, the family of triangles. So now on a general metric space, we want to do the same thing. We say that the space has bounded integral curvature if every point acts as a neighborhood such that for any finite collection of disjoint triangles, the sum their access is bounded by some constant. Now these two notions, actually they look quite different because in this case you're looking at the area, right? The area is kind of involved, but there you do not even talk about area. Is that everything I need? Oh, right. One last thing is that our project proves that a cat kappa, if you have a surface, a topological manifold, a surface that is cat kappa, then it has bounded integral curvature. So we prove this direction. But the other direction is simply not true. An example would be the surface of a cube. That's the best cube I have drawn here. Alright, so if you consider the surface bounding a cube, at the vertex points, so if you have a triangle here, the only triangle that has non-zero deficit is a triangle that encloses a vertex. Because I think you can show that each angle is 90 degrees, so the total deficit is 90 degrees. And if you have any other triangle, then you will have zero deficit, because you can kind of just like unfold it, and then it looks like a plane. So basically, this shows that the surface has bounded integral curvature. However, it is not cat kappa. Why? There's another kind of equivalent condition of cat kappa, and we never talk about. That's proven by Alexander Rolf in the paper we showed you earlier, in his like 1957 paper. So basically, if you take a sequence of triangles shrinking to a point, and you look at the ratio of the angle deficit with the area, then this will be bounded by kappa, by the cat kappa definition. So, however, if you look at families of triangles shrinking to the vertex point, the deficit is constant, but the area goes to zero. So this is not bounded, and the surface doesn't have is not cat kappa. All right, so now let's present the actual proof.
Yeah. So before discussing the full proof, I'll talk about a few lemmas that we showed. A few things that we discovered. So the first thing we discovered was that if you start with any geodesic triangle in a cat kappa space, PQR, and if you draw a segment from one of the points to the opposite edge, then the excess of PQR, so let T be PQR, the excess of T, sorry, thank you. So if you have a geodesic triangle PQR and you draw a segment from one vertex to the opposite edge, then the excess of the original triangle is less than or equal to the excess of the two subtriangles that get generated. And this is, well, what is excess, first of all? It's just the sum of the angles minus 180 degrees. So this angle is smaller than or equal to the sum of these two angles. And this angle is pi, which is less than or equal to the sum of these two angles. And so you could sort of do some algebraic manipulations to show that this follows. Yeah. Another thing we discovered about this kind of vertex-edge connection is that the model area decreases. So what do I mean by that? So if you have the original triangles, PQR and this segment, and then you look at the model space, let's say the model space is a Euclidean plane. So I'll draw straight lines. Basically, the Kappa condition implies that distances in Kappa are smaller than distances in the model space. And so if you looked at the comparison triangles for these two subtriangles, they would occupy a smaller area, smaller total area in the model space than the original triangle. And I'm not going to walk through the details of this proof. Right, so we have a tool which lets us increase excess while decreasing total model space area. And so, just erase off. So what do we actually want to prove? We want to show that given any point in a Kappa surface, there is a neighborhood about that point such that for any family of triangles that you draw in that point that are non-overlapping, the sum of their excesses is bounded by some constant. So what's that constant going to be? Well, we have that the neighborhood is has bounded area. So what we expect to get is that, and also on a sphere, we have that the excess of a triangle is just the curvature times the area of the triangle in the sphere. So what we expect to see is that the sum of the excesses is less than or equal to Kappa times some notion of area of the neighborhood. So if we consider a point and a neighborhood about it that is homeomorphic to a disk, we don't know exactly how to relate the Hausdorff 2 measure of we don't know how to relate the area of this neighborhood to excesses, but we do know how to relate areas of triangles to excesses. And it turns out, based on a paper written by our mentor Matthew Romney, any point has a neighborhood consisting of triangles, a background triangulation. And so instead of looking at the original neighborhood, we could just look at the neighborhood consisting of those triangles. And a simpler case is just if the neighborhood is just a single triangle. So if a point on a Kappa surface has this neighborhood, and we consider any family of simple triangles in that neighborhood, Let me actually make this bigger. How much time do we have? So let this triangle PQR, let's just call it B for background triangle. So the area of this triangle in the model space, you can consider its area. So B bar denotes the area of the comparison triangle in the model space. So how are we going to use like these tools in order to get this inequality? Well, first of all, I should draw like an arbitrary family of triangles, right? So suppose we have this triangle and this one, T1 and T2. So it turns out we discovered like a process which gets us both of these properties. So here's how the process works. We start with the point P, and consider all of the vertices of T1 and T2 and connect. There exists a geodesic segment connecting these 2 points, and then you can extend that geodesic to QR. And yeah, this shows what that looks like. And then the next step.
On this laser.
Yeah. So the point of this first step is to, well, the point of this overall process is to get a vertex edge triangulation, something where we can apply these properties inductively. And the point of this first step is to, this shape only consists at this point of triangles and quadrilaterals. And then the next step is, since it's only quadrilaterals that have more sides than triangles, we just connect their diagonals. And so this entire figure consists of only triangles. And so it's a triangulation of the figure, which could have been drawn by connecting vertices of triangles to opposite edges. So how could that figure have been drawn? Well, first we could have connected all of the segments from P to QR. So this connects this vertex to the edge QR, and so on. And then considering the parts of each of the family, each of T1 and T2 that occur within these long triangles, we can connect this vertex to this edge, and then this one to this one, and connect them in a certain order. And then repeat for the whole thing. And I guess I should clarify. So like, what's the actual point of this? If you draw one more segment from, say, this vertex to this edge, then we can then say, so we have the excess of T1 and the excess of T2, but this splits T2 into like T3 and T4. Which have, again, a greater sum of excess. So what we're really doing here is we're inductively applying this lemma, and then later the area in decreasing lemma.
Yeah, I didn't put the equation. Sorry.
Oh, okay, that's fine. So the excesses of the T1 and T2 are smaller than the excesses of each of these subtriangles that occur within them. And this is because if you have a triangulation of a triangle where all of the vertices of the subtriangles like occur on the edges of that triangle, then we can also say that the excesses can only increase. So I'm just letting SI denote the subtriangles that occur within T1 and T2. And then if you relate back to the model space, we know that since angles on a kappa surface are smaller than angles, the angle between the two geodesics on the comparison triangle model space, we can say that if you draw like these triangles in the model space, you get that not only are the angles smaller, but the excesses are also smaller, because the excess is just the sum of the angles minus pi. So triangle excess smaller than comparison triangle excess. And the sum of the excess of a triangle in the model space, so for example on the sphere, is just this curvature of the sphere times the triangle's area. So this is equal to, I'll write it here. This is equal to curvature times areas, and you can factor out the curvature. But the SI are only the subtriangles that occur inside the T1 and T2. But there are other triangles in this figure, and the area of a subset of those triangles is smaller than the area of all of the triangles. So this is less than or equal to kappa times the sum all I did was I changed M to P. Yeah. The SI are a subset of all of the subtriangles in this figure. And since this figure could have been drawn by repeatedly connecting a vertex to the opposite edge and repeating, we get to apply the property that model area decreases each time you do one of those connections. And so this quantity, by induction, is less than kappa times the area of the model triangle for this big, larger triangle. And the model area of the larger triangle does not depend on T1 and T2. It doesn't depend on the collection of triangles that you draw inside. So in the case where the point has a neighborhood where you could draw just a triangle around it, and in the case where that triangle is a neighborhood, then the sum of the excesses of any family of triangles, non-overlapping, drawn within that neighborhood, is bounded above by kappa times the model area of the overall triangle. And that's our constant for the bounded integral curvature.
Alright, and I just wanted to say, like, there is some significance to our result. In particular, sorry, maybe I shouldn't erase this. Maybe I'll erase this. So first of all, this is not the only way of proving this statement. Actually, our mentor has worked on like 2 separate proofs that kind of involve like another subdivision process, but in a different way, and another one another one that involves like approximating your surface by surface of bounded integral curvature, and then finding like a map between them that can preserve area and curvature in some meaningful way. But the real significance is in this kind of this this other thing, which is a equivalence of metric surfaces, where you have stronger implications going to things that are almost like the lowest cost of generality of surfaces. Sorry, most general kind of surfaces before you kind of get to fractal surfaces. So I might as well write it out. So you have Riemannian two manifolds. These are the most well-studied kind of smooth surfaces of curvature less than or equal to k kappa. And then you have your kappa surfaces. And then you have the surfaces of bounded integral curvature, and this is the implication that we proved. And then way down here, you have like properties such as having, this is a property, the technical name for it is called locally finite Hausdorff 2 measure. Yeah, okay, and actually, so and there's a paper by these guys called Constantine and Lafont. And they got like a $220,000 grant from the NSF. And what they basically proved is that a surface that's kappa has this property, but if they knew this, then they actually wouldn't need to spend the $220,000 on their research, and they could have just cited us. So anyways, did you guys have any questions?
So they should have given you the 200.
Yeah, they should have given us $220,000. Alright, so it's more of a joke, but...
So this result is kind of like a Folk theorem. So we read a paper.
Yeah.
It seemed like early
2001.
Oh yeah, early
Yeah.
2000. They
And-
claim there's a proof, but it's not actually there. Like we think you just can't wait. There's no meaningful thing there. And then I think in 2013, some person
Thomas Richard, yeah.
Math Overflow
Oh,
posed a question. Let's say I was writing a literature review for the field, and I think this result is kappa implies doubling curvature would be interesting. I see statements referring to it, but there's no proof. Like, could you find me a proof? And somebody point into a preprint that's still not out there, like to this day. So it seems to us that the proof is not there; it's just missing, and we figure out kind of like elementary way to prove it.
Yeah, and yeah, we are actually trying to write a paper, but we're not like 100% like ready to actually do it yet. So, anyways, do you guys have any questions?
Well, actually, are you guys interested in like doing an RU?
Yeah,
I think we can.
want to ask questions about
Yeah.
doing an RU.
I think we can talk a little bit more about it.
Yes, so-
Structure.
Yeah. Around how much did you, before the RU began, how much backgrounds, like did they give you a set of things that you should read ahead of time to be prepared, or?
Yes, so actually we participated in an independent study with Professor Yushen Wu and Professor Matthew Romney, and they kind of guided us in the study of surfaces, basically, but like from all these different kind of perspectives, like topological, a little bit of like differential geometry, and also like some, actually even like from this kind of like, there's actually like these certain like group theory perspectives you can have on surfaces, and I took a brief look at that as well. Yeah.
So yeah, so we have an independent study course during this spring. So we pick a book. It's called Mostly Surfaces, and each week we have a Zoom meeting. And each of us will present one chapter, just talk about interesting theorems, maybe do a few exercises. But according to what I see, I think the book basically covers, the first part are mostly covered in the graduate courses. So I think but before that, I don't think you need much to like get into the project.
Yep. Also, this is a pretty good program, I would say. Just the program is you have a lot of opportunity because it's fully funded. You get your housing paid, you get your food paid, you get to go to a conference, you get like this other trip. The other thing that's actually more also relevant, I'd say, is that for international students, actually, this is like one of the only programs in the United States because the majority of them are funded by this organization called the NSF, the National Science Foundation. And of course, that's a United States government organization. It's not going to just give money to like international students all the time, and basically it doesn't do that. So yeah, the Stony Brook program is actually pretty unique in offering that opportunity for international students as well.
That's true.
Alright.
Yeah, and I think if you are considering, I don't know, pursue further study, maybe like doing a PhD in mathematics or related fields, I think it's good to do the REU.
Yeah.
Actually get your hands dirty.